Hello guys, nice to see you. How are you doing?
Good afternoon.
Hi. So last time we introduced a new state parameter, which is entropy, and considered it from the point of view of macro state, and got the right equations for determining change of entropy for different thermodynamic processes in ideal gas. So isobaric, adiabatic, isothermal, and isochoric. So as I mentioned last time, during this discussion, we will consider entropy from the point of view of microstates and so-called statistical weight, which is which defines the total number of microstates with which you can define macrostate. So that will be considered an example of ideal gas also. And that will show us the relationship between entropy and number of microstates which are necessary to define the macrostate. Under microstates, we understand parameters which describe individual atoms or molecules of ideal gas in terms of their location in certain volume. So in terms of probability of occupying a certain micro volume in this container. So let me switch our slides. And we will consider such a system, which is quite familiar to us already, cylinder with some piston. Keep in mind that all walls are thermally insulated. We consider that they are thermally insulated. Here we have some membrane. And in the lower part, under this membrane, we have ideal gas. And here, like above the membrane, in the gap between membrane and the piston, there is actually nothing. So vacuum. So initial volume we can mark as V initial, and like full volume without membrane we will mark as V final. So let us consider the number of microstates which can describe the first initial macrostate of the ideal gas, considering the variety of molecular locations available to the molecules. So let's assume that each molecule occupies some microscopic volume Vm. So that is volume which like very tiny microscopic volume of the molecule itself. The total number of possible locations of a single molecule in a macroscopic volume is defined by omega, like small omega I, equals to V initial, its total initial volume when the membrane is in place, divided by this microscopic volume of the molecule itself. So with this, we can consider also two molecules. There, if we, first molecule, if we have two molecules, and first molecule has Wi options to locations to occupy in this initial volume, and the second molecule will have again the same probability, like the same number of points to occupy in this initial volume Vi. So we neglect with the probability, very small probability, that two molecules will occupy the same position, micro volume. So with this trend, we can expand it to n molecules in the initial volume, and total number of microstates to allocate these n molecules in initial volume will be defined then by W, capital W I. It's in initial volume. I stands for initial. There will be omega I in the power of n. So we define that each molecule can occupy Wi positions. So n molecules will occupy Wi in the power of n. And again, we assume that molecules do not occupy the same micro volume. So we can write in this case that we will have Vi divided by Vm, micro volume, in the power of n. So what will happen if we take away this membrane? So molecules, then let us show it here. And we have the same number of molecules n, but they will occupy evenly all volume of the container. So then we need to operate with, instead of Vi, with V final. So W final means the total number of microstates which can describe the given macrostate when we occupy already all volume of the container, will be equal to W final in the power of n, because we still have the same number of molecules n, and that will be equal to V final divided by Vm, which is microscopic volume of the molecule itself, in the power of n. So this W, capital W, is actually so-called statistical weight or thermodynamic probability, which defines the total number of microstates to describe a given macrostate. So we have these two values for statistical weight W final and W initial, we see that because of V final is larger than V initial, then we will have more like higher number of microstates to describe final macrostate in comparison to initial macrostate. So taking this into account, we can also consider now what will be the ratio between WF and WI. So WF divided by WI is equal to V final divided by Vm in the power n divided by V initial divided by Vm in the power n. And that will result in V final divided by V initial in the power n. So now let us maybe write this part on the new slide and continue. So we got that WF over W initial is equal to V final over V initial in the power n. So now let us multiply these left and right sides by Boltzmann constant. So K here and K here. Taking and also actually it would be better if we consider first taking natural logarithm and then multiplying by K. So let us take natural logarithm of left and right side and multiply by K, by Boltzmann constant. So we will get K times natural logarithm of W final over W initial. That will be equal to Boltzmann constant times natural logarithm of V final over V initial in the power n. So we can take it like this. So now taking into account the properties of natural logarithms, we can get this n, which is the power, as a coefficient in front of the natural logarithm. So it will be K times n times natural logarithm of V final divided by V initial. We can represent number of molecules n as number of moles times Avogadro's number. So it will be K times nu, number of moles, times Na. And here will be natural logarithm of V final divided by V initial. So now, if you remember from our previous discussions, what will be the product of Boltzmann constant and Avogadro's number? So these are two constants, means we will get another constant. And what's the name of that constant? We had that in when we considered the equation of the state of ideal gas.
You mean the universal gas constant?
Exactly, yeah. Product of Boltzmann constant and Avogadro's number give us universal gas constant. So we can actually write that it will be equal to mu times R, number of moles times universal gas constant, times natural logarithm of V final divided by V initial. So with this, we finished our derivation. What we can do here, we can write in another form this first term, like left side. It will be k times natural logarithm of W final statistical weight of the final macrostate minus k natural logarithm of W initial. That is equal to mu times R natural logarithm V final divided by V initial. Okay, this we remember. So that gives us the relationship between the statistical weight. Actually, it's changed from initial to final state and initial and final volume of ideal gas. So this we keep in mind. And next step, we need to define what will be the change of entropy. So we will come back to this. Excuse me. We will come back to this slide a bit later. Now, let us consider the process which will happen when we eliminate this membrane. So we mentioned initially that walls of the container are thermally not conductive. So means there is no exchange of energy through the interface of this container, this volume with external environment. And another thing which is important to mention when we consider change of internal energy of this system. So for Q, it's equal to 0. There's no heat exchange, but we also have work. Work here also is equal to 0 because we have expansion in the free space. So work is defined as pressure times dV. Since we have, like initially above the membrane vacuum, there is no pressure, this work done by expansion in free space is equal to 0. So change in the internal energy of such system will be equal to 0, means that temperature remains constant. From our previous discussion last time, we considered change of entropy, delta S, for different thermodynamic processes. And when our temperature was constant, we could write that this is equal to S final minus S initial is equal to mu times R times natural logarithm of V final divided by V initial, right? V initial. So where we get it from, you can double check. We derived some equation for the change, like for the differential of state parameter entropy, and there were two terms. One term responsible for the contribution in change of temperature, another for change in volume. Since temperature remains constant, we have only change in volume. So that is the term which we get after integrating the differential, assuming that temperature remains constant. So looks like we have change of entropy defined by this equation. So if we look back on our previous slide, we see this equation in the right side of the previous equation. Means that this actually is equal to change of entropy. So change of entropy is equal to this difference of natural logarithms of statistical weight or number of microstates which can describe the given macrostates final and initial, and relates entropy with this statistical weight. So we can write now that K times natural logarithm W final minus K natural logarithm W initial is equal to S final minus S initial equal to delta S, which is change of entropy. So according to this statement, we can write that entropy is defined as K Boltzmann constant times natural logarithm of statistical weight or number of microstate parameters which are necessary to describe the macrostate W. So that is the relationship between entropy and micro parameters of the system. And also, since we expressed this second law of thermodynamics in terms that delta S is always larger or equal 0 for any isolated system, so equals 0 for reversible and larger than 0 irreversible processes. We can also interpret it from point of view of microstate parameters. Every time when system goes to some thermal equilibrium condition, the statistical weight increases because the number of possible microstates which describe the macrostate at equilibrium condition is larger. So means that all thermodynamic processes in isolated system should follow that, should happen in that direction, which causes the increase of statistical weight. or increase of number of microparameters which describe the macro state. So that is also interpretation of second law of thermodynamics from a microstate point of view. So we can proceed further with considering this micro state parameters and change of entropy. So change of entropy, as we already wrote here before, final minus initial is equal to k natural logarithm W final over W initial. So we can put back this difference, represent difference in logarithms as logarithm of the ratio. So now we can consider a bunch of different processes. So first, let us define just WF over W initial. That will be exponent of delta S divided by K. And we remember that delta S by definition is equal to integral from initial to final state of dq over t. So we can write that it will be equal to exponent 1 over k times integral from initial to final state dq over t. So we also considered what will be this integral in details for different thermodynamic processes in ideal gas. So that's why the ratio of statistical weight for final and initial states. In general, if we consider first isobaric process, P equal constant, then you remember why we consider isobaric process first, because for isobaric process, we have both heat transfer and work done. So in that case, this ratio of thermodynamic probabilities or statistical weights is defined as exponent. Then we have this k in numerator, and in denominator we should have these two components responsible for change of entropy because of change of temperature and change of volume. So we can write here CV times nu, number of moles, times natural logarithm T final over T initial. Here we also need to divide it by K because we have this K here. And plus nu times R divided by K times natural logarithm V2 divided by V1. V final divided by V initial. So you understand what we are doing. So we have this integral here, which stands for change of entropy. And this integral from initial to final dq over t is equal, we have shown this previously, is equal to CV times nu natural logarithm T final over T initial plus nu times R natural logarithm of V final over V initial. So that we have shown for isobaric process. Now we have just here additional K in the denominator. And that's all. So that's where we got this expression for the integral which defines change of entropy. So now this is given for isobaric process, but we still have a bunch of other processes which should be considered. So let's say isothermal process, T is equal to constant, then we don't have this component because change of temperature doesn't happen. So in that case, we can write that V final, W final over W initial is equal to exponent of mu times R divided by K natural logarithm V final over V initial. Now, if we recall that the ratio R universal gas constant divided by K Boltzmann constant, that should give us, let's show it like this, that should give us Avogadro's number. And also we remember that Avogadro's number, that is, by the way, definition of Avogadro's number. What is that?
Number of particles in 1 mole of matter.
Okay, that's good. So now we have number of moles nu times Avogadro's number, and that gives us the total number of particles or molecules in our container. So we can write exponent n total number multiply natural logarithm of V final divided by V initial. So that is, so taking into account these properties of logarithm, this n in front of logarithm can go to power of the argument of the logarithm. So it will be V final over V initial in the power of n. And if we take exponent of natural logarithm, it will give us the argument. So that will actually be V final over V initial in the power of n. Or we can represent it as we did before as unity plus delta V over V initial in the power of n. So that gives us the ratio between statistical weight of the final and initial states for ideal gas under isothermal process. So we can also write for isobaric process. So for isobaric process, W final over W initial, that is equal to, can be represented as unity plus delta T over T initial in the power C CV times nu divided by K. So that is the expression for V equal constant. So summarizing our discussion, we introduced the definition of entropy from point of view of microstates. And in order to do that, we introduced the statistical weight, which stands for the number of microstates necessary to describe a given macrostate. Consider these statistical weights for final and initial conditions of our model system, some thermally isolated cylinder with a membrane inside. We have shown that statistical weight for final state, macrostate, is larger than for initial because final volume is larger than initial volume, and found the relationship between the change of statistical weight and change of volume of this system. So based on previous discussions, we have used this previously derived equation for change of entropy when we don't have any change of internal energy, means constant temperature. And we figure out that the equations for change of statistical weight and change of entropy, actually, they can be described by the same equation, nu times r, natural logarithm of V final divided by V initial. So by equating them, we can show that this direct relationship between entropy and statistical weight. And we also can describe second law of thermodynamics in terms of claiming that all thermodynamic processes in isolating system, they run in that direction, which causes the system to come to some macro state with larger statistical weight. That is true for all states under thermal equilibrium. So also we described how the ratio of final and initial statistical weights of this ideal gas will be possible to calculate for different thermodynamic processes in ideal gas, for constant pressure, constant temperature, and constant volume. If you have any questions, you're welcome. So I will remind you that on Monday, we have the final exam. So we will discuss this also in more details on our next meeting on Friday. But just as a short reminder, on Monday, final exam, which will, because I received recently some questions regarding chapters which will be covered by final exam. Final exam will cover all chapters. There will be a bit focus on thermodynamics and molecular physics, since these chapters were not covered by previous midterms. However, besides that, there will be problems from any chapters covered by our course. So that's why please take your time and repeat all chapters, main statements, main equations, so you come to the final exam prepared and with refreshed memory about all chapters covered in our course. Okay, then thank you for your attention, and see you next time on Friday.
Thank you. Goodbye.
Thank you. Bye.
Okay, bye-bye. Take care.